Hello, AP Physics. In the last video you watched, you learned about derivatives and kinematics. In this video, I'm going to show you what integration with kinematics looks like and how you can use it in some simple ways for the future. So we're going to start off with velocity. Now, velocity, we learned, is also equal to the change in our position over the change in time. Another way to think about this is that for every single second, we gain 5 meters. If I want to know how many meters I move in 3 seconds, I need to sum up 3 5s together. So another way we can write this as the change in x is equal to the sum. I know that looks like a 5. I'm sorry. 5 times the change in time. So now that we have this equation of sums, what does this actually mean? So we can represent our velocity using a vector. So each time we have 1 second that passes, and then another second. This is the second, right? And the third. But each time, this is 5, this is 5, and this is 5 meters per second. So altogether, when we do the sum, we end up with 15 meters. This makes even more sense if we look at our graph. So here again, I have my 3 different vectors. They're essentially all the same length. But if you take a look at this, you'll notice that the area underneath my curve here is an area of 15 meters, right? I am multiplying 5 meters per second by 3 seconds, leaving me with 15 meters. When we integrate, we are essentially looking at the area underneath the curve. Now, this can be a little confusing, as I'll show you next. So what about this graph? We see that we have an area of 4, but our 2 is a negative. So this means that we actually have an area that is -4 meters, which is strange, right? Area should always be positive, but at integration, since it is underneath the zero, we're going to end up with a negative value. And so we actually move backwards. We see that we have a negative displacement. We move backwards here. So in that past slide, we saw that we have a negative area. But what happens when we combine it with 2 different kinds of areas? What amount of displacement do you think we have here? So for the first one, we have -4, and in the second one, we have 15. Take a moment, think about an answer. We should have a delta x of -4 and 15 added together, which leaves us with 11 meters. For this problem, I want you to try this on your own. So take a moment, think about what it is, pause the video so that you can write down your own answer. You should end up with a value of -1 meters for the displacement. So this next one is a little bit more tricksy. We have a negative area, but we also have 2 positive areas that are overlapping. Take a moment, try to figure out what that displacement is going to be. All right, so that first box is a -2, just like it was before, but these 2 overlapping ones we can just treat as 2 rectangles up against one another. So we have a 2 times 5 gives us 10, and a 2 times 6, which gives us 12. The 2's cancel out, so we're left with a displacement of 20 meters. Now, in integration, we don't use the sum symbol like we were before, the word sum. Instead, we use this kind of long S. And this represents the sum force. So if I wanted to know what the displacement was, I could write it out as delta x equals this long S, 5 delta t. But the delta t isn't the most accurate. Actually, what we should be writing it as is delta x equals the integral of 5 dt. Now, the letter lowercase delta, which I'm calling d, lets us know the instantaneous amount of change at that point. Now, 5 is a constant, so we can actually pull it out front, so we can make this a little simpler. So it's going to be delta x equals 5, the integral of dt. I'm running around a room a little bit here, so I'm going to scoot this up and into the middle. That way we can see it a little better. Now, as we just saw, we simply multiply by the amount of time. So if I'm doing this integral, the integral of dt is just t. So the change in x is then equal to 5 times the change in t. And we want to know about it between a particular interval, and that was at the very beginning. If you could think back to that first problem, we were thinking about it from time 0 to time 3. And we'll put our units on there. So when I plug this in, I want the difference between the final value, this 3 seconds, and the initial value. So I'm going to move this up just a little bit more. So delta x is 5 times the difference of 3 seconds minus 0 seconds, which is, of course, 3. So when I multiply 5 by 3, I get my 15. Now, all of this is a lot of steps to explain what an integral is so that you can see all the different components. Remember, I talked about the integral being the area under the curve. It's also a summation, right? It's a summation of the 1 second and the second and the third second all together, which gets us that 15. So just in general, delta x is equal to the integral dt, which in our case, the integral of dt gives us time. All right, but what happens if we have delta x equals the integral of t dt? What happens then? Well, it would seem like we would get the same integral together, so it would be t times t, giving us t squared, right? This seems simple enough. But it is not the case. Let's look at the graph on the next slide. Just like I said previously, the integral is the area under the curve, and in this case, the area under the curve makes the shape of a triangle. If I want to know that area, I'm going to need the equation for the area of a triangle, which is 1/2 the base times the height, right? But since we know that the equation of our line here is t, and that means that the base has length t and the height has length t. Notice here, right, at time 1, we have a velocity of 1, and at time 2, we have a velocity of 2. So this means that the area is 1/2 t times t, or 1/2 t squared. Now this might start looking familiar to our equation that we have for position with respect to the acceleration portion. So just for your notes, if I want the change in x, I'm going to do the integral, and let's say it is t dt. We now know that that is going to give us 1/2 t squared. Let's take a moment. Let's try another one. Let's say we have the integral of t squared dt. What do you think we're going to have then? If we were to look at the graph and go through it, which I'm not going to do at this moment, we would find that it would be 1/3 t cubed. If I was going to do the integral of t cubed dt, I would find that I get 1/4 t to the 4th. You might start noticing a pattern at this point, and I'm going to write that just below. So if I'm doing the integral of t to the n dt, I am going to find that I have 1 over n plus 1 t to the n plus 1. So if you're doing integrals in physics, just with some basic powers, this is how you're going to do it.